In this lesson, we will go about formally proving reciprocity theorem for resistive networks. Okay. In doing so, we will recall some other properties that we have seen for resistive networks earlier. Okay. Now, first let me make a distinction between two kinds of two ports. This is the picture I have been drawing so far, 1 prime and 2 prime. Okay. Now, a subset of two ports can be of this form 1, 2 and this 1 prime and 2 prime are really the same terminal. Okay. So, this is the common terminal and port 1, port 2 and a common terminal. Okay. Now, this is a more general representation, but a number of two port networks fall into this category. Okay. So, first I will take this type of two port network, prove reciprocity and then extend it to that one. Once we do it for this, it turns out to be trivial for the other case. Okay. It turns out to be a lot easier for this, given the kind of circuit analysis we have already studied. Okay. Now, this is known as a 4 terminal 2 port and this is known as a 3 terminal 2 port. Okay. Now, to go about proving reciprocity, I will use this picture. Okay. So, 1, 2 and the common node. This is the first port, this is the second port and I think of both ports being excited by current sources I 1 and I 2. Okay. So, this corresponds to the Z parameter picture of the 2 port. Now, like I earlier showed, if you prove reciprocity with Z parameters, then that means that all the other parameter sets also have the corresponding reciprocal relationships. Okay. So, it is the network that is reciprocal. So, you can prove reciprocity by proving the reciprocal relationship for any set of parameters. That is, you can prove Z 12 equals Z 21 or Y 12 equals Y 21 or H 12 equals minus H 21 or G 12 equals minus G 21. Any of them implies the others. Okay. So, we will start with this. By the way, the most important thing, this network now consists only of resistors. Okay. Okay. So, that is important. Now, let me try and use nodal analysis for my proof and I will choose this common node as the reference node. Okay. So, then the port 1 voltage V 1 is nothing but the voltage at this node and port 2 voltage V 2 is nothing but the voltage at this other node with respect to the reference node. Okay. So, now if I set up the nodal analysis equations for this, let us say that inside there are a number of nodes. Okay. Let us say that there are a total of n plus 1 nodes. Now, I choose it to be like this, so that I have n equations. I exclude the reference nodes and I have n nodal equations. Okay. Now, the two nodes corresponding to the two ports, I choose to label them node 1 and node 2 and the remaining nodes in the circuit are labeled 2 to n. Okay. And there are only two independent sources in the circuit I 1 and I 2, because inside we have only resistors. Okay. So, now clearly the nodal analysis equations for this can be set up as some G matrix times the unknown voltage vector equaling the independent source vector, which consists only of current sources in this case. Now, recall that when you have only resistors and current sources, nodal analysis was easiest, and also the conductance matrix had some nice properties. Okay. So, this conductance matrix was symmetric when we had only resistors and independent current sources. Okay. So, we have a symmetric conductance matrix. Now, let me sort of write this in an expanded form. Okay, I have my G matrix here and I have my voltage vector V 1, V 2, which correspond to the 2 port voltages, and after that I have V 3 all the way to V n. Remember, this is an n plus 1 node circuit. So, there are n node voltages and n independent KCL equations. Now, this equals the source vector, and what we have in the source vector is basically the independent current source value being injected into a particular node. So, clearly into node 1 we are injecting I 1 and into node 2 we are injecting I 2. Okay. And the rest of the entries here will be 0, because we have no other sources in the circuit. Okay. Now, what do we need to prove reciprocity? Let me copy this over. Okay. The Z parameter description of this network would be Z 11, Z 12, Z 21, Z 22 times I 1, I 2 equals V 1, V 2. Okay. So, we can see parts of this here. We have this I 1 and I 2 over there, V 1 and V 2 over there, but we have all these extra variables which we have to eliminate and come up with a relationship of this type to see if the network is reciprocal. Okay. To do that, what I will do is the following. This G matrix I will subdivide into 4 parts. Okay. So, that is, here I have taken 2 rows and 2 columns. Okay. So, let me write down the numbers. This is 1 and 2, and then I have 3 all the way to n. And similarly, I have taken 2 columns 1 and 2, and then I have 3 all the way to n. Now, I will have basically 4 sub matrices in each of these. Okay. So, let me call this G A, whatever goes into the first 2 rows and first 2 columns. So, clearly G A is a 2 by 2 square matrix. Okay. Now, here I will have G B. G B is in general broader than it is tall. Okay. It is a rectangular matrix and it has 2 rows and n minus 2 columns. Okay. And in this location I will have G C, and G C will be taller than it is wide. It will have n minus 2 rows and 2 columns. It is also a rectangular matrix. And finally, G D, which is a square matrix of n minus 2 rows and n minus 2 columns. Okay. Now, the important part, if we have a circuit with only resistors and independent current sources, we know that the G matrix is symmetric. Now, what does it mean? If the G matrix is symmetric, that is about this diagonal we have symmetry. So, that means that GA and GD are also symmetric square matrices. Okay. Because the G matrix is symmetric, GA and GD are also symmetric square matrices. Okay. So, GA and GD are also symmetrical, and also because this G matrix is symmetric, this GB and GC are not independent of each other. Okay. So, it is very easy to see that these two are related by GC being equal to GB transpose. Okay. So, the symmetry of this matrix means that GC will be the transpose of GB. Okay. So, with this we can go ahead and try and come up with a relationship of this type involving only two variables V 1 and V 2. Okay. What I will do now is to split up this one with two different variable vectors. Okay, you will see what I mean. First, I will write G A times V 1 V 2 plus G B times V 3 all the way down to V n will be equal to I 1 I 2. Okay. So, essentially what I have written are the first two equations. Okay. So, the first two equations or the first two rows will correspond to this equation, okay, because we have only this part of the matrix coming into picture. Okay. Now, if you are a little confused about this, you can consider some matrix with individual entries and write it down and see. Okay. So, G A will multiply this part of the unknown vector and G B will multiply that part of the unknown vector. Okay. So, these are first two rows or the first two equations. Okay. Now, I will write it for the remaining ones and I will also use the fact that G C is G B transpose. So, G C will multiply this vector V 1 V 2 and G D will multiply the rest of this unknown vector. Okay. So, we will have G B transpose times V 1 V 2 plus G D times V 3 up to V n being equal to a vector of all zeros. Okay. And these are the last n minus 2 nodal equations. Okay. We have the first two nodal equations over here and the last n minus 2 nodal equations over here, and because of the way we chose the node numbers, all the independent sources appear in this part and nothing is here. And what we wanted to eliminate was this extra unknown variable vector V 3 to V n, and that we can do by using the second equation. So, this from this one we have essentially I solve for this unknown vector. Okay. So, I will get that extra unknown vector V 3 to V n to be minus G D inverse times G B transpose times V 1 V 2. Okay. That is, we have got this unknown vector in terms of the desired vector V 1 V 2. Okay. Now, what I am going to do is substitute this into the first two equations. Okay. Is this clear? So, then essentially I have to substitute this over here. Okay. So, this is where I have the extra unknown vector. So, if I do that, I will get G A times V 1 V 2 plus G B times the extra unknown vector, which we saw was minus G D inverse G B transpose times V 1 V 2 and the whole thing equals I 1 I 2. Okay. Now, I have this relationship G A minus G B G D inverse G B transpose. This whole thing is a 2 by 2 square matrix. G A is 2 by 2. Okay. G B has 2 rows and n minus 2 columns. G D has n minus 2 rows and n minus 2 columns, and G B transpose has n minus 2 rows and 2 columns. So, finally, you will end up with 2 by 2. Okay. This whole thing times this vector V 1 V 2 equals I 1 I 2. Okay. Now, this is the relationship for this particular circuit, and you see that already this is the Y matrix, Y parameter matrix of the circuit, right, because in terms of Y parameters we would have the Y parameter matrix times V 1 V 2 equals I 1 I 2, and if we want the Z parameter matrix we have to invert this. But of course, most importantly what we want to see is this matrix symmetric. If the Y parameter matrix is symmetric, obviously the inverse Z parameter matrix will also be symmetric, and either way we have already proved reciprocity. Okay. So, to prove reciprocity we have to prove that y 1 2 equals y 2 1 or z 1 2 equals z 2 1, that is the Y parameter matrix is symmetric or the Z parameter matrix is symmetric. Okay. So, now let us look at this G A, it is symmetric, we know that comes straight from the symmetry of the G matrix. Now, what about this part? How do you prove symmetry? A matrix is symmetric if its transpose equals the matrix itself. So, that we will test. Okay. So, let us transpose this G B G D inverse G B transpose is our matrix A, and we transpose that. And you know that when you transpose a product of matrices, you will get the product of transpose of individual matrices, but in opposite order. Okay. So, first we will get this one G B transpose and the transpose of that. Next we will get that which is G D inverse and the transpose of that, and finally we will have G B transpose. Okay. And clearly this is G B transpose and transposed again. So, that is equal to G B itself. Now, this G D itself is a symmetric square matrix. So, its inverse will also be symmetric. Okay. So, when I transpose G D inverse, I will get the same thing, because G D inverse is also symmetric. And finally, I have G B transpose. So, the transpose of this is exactly the matrix itself, because that is the matrix I started off with, right, G B times G D inverse times G B transpose. So, this is also symmetric. Okay. And now, we have the sum or difference between two symmetric matrices. So, that also is symmetric. So, this whole thing here we have proved the symmetry. So, that is symmetric, and that is nothing but the Y matrix of our circuit. So, that is symmetric, which means that the two port network is reciprocal. Okay. So, the conclusion is that the Y matrix is symmetric and which means y12 equals y21, and hence it is reciprocal. And y12 being equal to y21 automatically means z12 being equal to z21, or h12 being equal to minus h21, or g12 being equal to minus g21. Okay. So, all of this automatically come from that one. So, using our knowledge of properties of the conductance matrix that appears in nodal analysis, we are able to prove that a resistive two-port network is reciprocal. Of course, we have restricted the kind of two-port networks. We have taken only a 3-terminal two-port network, but it can be generalized to arbitrary two-port networks, that is 4-terminal two-port networks in a very simple way. Okay.